So, good evening. Yes, I will present the Planck results, the cosmological results that the first release was published last year. So, okay, this is the outline of my talk. So first I will present briefly the Planck mission, then data, cosmological parameters, something beyond the standard model, contaminants and secondary anisotropies, some anomalies found even previously by WMAP, and the next step, which is polarization. So this is a picture of the Planck mission. This is a medium-size mission launched in May 14th, 2009 to image the temperature and polarization of the CME over large areas of sky in a large frequency range in such a way that the limitation would be the sensitivity and our ability to remove foregrounds, astrophysical foregrounds. It is led by two consortia, each for each instrument, and is the low frequency instrument, whose PI is Renaud Mandoresi from Bologna, and then the high frequency instrument covering the low frequency one, this from 30 to 70 gigahertz, cool at 20K, and the high frequency one is from 100 and almost 900, cool at 100 milli-K. And the PI is Jean-Luc Pouillet from Orsay. So the nominal mission was envisaged for 15 months, 2 full sky surveys. But due to the successful of the nominal mission, is extended the mission for longer, and the end of operations was last October. So this is a picture of the a cut, in fact, of the high-frequency instrument, where you can see all the volumeters there, cool at 100 milli-K, and all the horns and different stages of cryogenics. And this is a similar picture for the low-frequency instrument, which is a completely different technology. It's based on low-noise amplifiers, and the signal is passed through what is called the radiometer chain, and is detected in the backend unit. So this is the surveys performed by Planck. There are 5 common surveys covering most of the sky, in which the 2 instruments were working together. And then 3 extra surveys by only the LFI. So the nominal survey, whose temperature has been already analyzed and published last year, is for covering 15 months, 15 and a half. And the total mission with the 2 instruments is like 29 months. And Planck performance has been determined from the flight, not only from the ground. And these are the numbers you can see here for all the channels, number of detectors, angular resolution, which goes from 33 degrees to arc minutes to almost 4.5 arc minutes. And then the sensitivity, and you have here the best sensitivity for the cosmological channels between let's say 70 or 100 to 217 gigahertz. And then the others are to monitor the foregrounds, the galactic emissions. Well, in cosmology also we have an anniversary this year, which is the 50th, 50 years ago the CMB was detected for the first time with this horn here in Crawford Hill in New Jersey. So this is an interesting year, also for cosmology. And then we have here Planck as the 3rd generation of satellites. First one was, the COBE NASA one, which first detected the anisotropies at 10 degrees scales, and also provided a very good precision of the black body radiation. Then WMAP improved in sensitivity and resolution and determined much better the whole spectrum of anisotropies. And finally, Planck, which is supposed to be the ultimate mission for temperature. So with Planck, the idea is that every piece of information that can be extracted from the temperature of the CMB is in fact extracted. So these are the around 30 papers published already last year on cosmology. There has been also many other publications on astrophysics, astrophysical objects, like our galaxy or extragalactic sources, clusters of galaxies also. But here we have different kind of papers dedicated to the instrument here. Then the different foregrounds, cosmological parameters, cosmological constraints, and also some secondary anisotropies. These are the three topics that I'm going to talk most. So this is the data, so 9 frequency channels covering a very wide range of frequencies, which is very important to disentangle, to separate between the cosmic signal and the astrophysical foregrounds. In particular, here already you can see everything. You can see the CMB in temperature, the blue spots mostly here. Then you can see the galactic emission at low frequency, mainly coming from synchrotron and free emission. And then at high frequencies, you have mostly dust. So this is a very good monitor channels for the dust, in this case in temperature, but we also have polarization. And this is the power spectrum extracted from these frequency maps. And basically, you can see the data, which is very well fitted by this red line, mostly, especially from high multipoles, from 50 up. And this is supposed to be a very good fit to the standard model. And in particular, we can determine very well, is the best determination of the 6 parameters characterizing the standard model. So we have here the baryonic physical density, the color matter density, the angular scale of the sun horizon at recombination, optical depth, scalar spectral index, and the amplitude of the fluctuations. So Planck data are extremely well described by the standard spatially flat lambda ACDM model. The best determined parameter is the angular scale of the sun horizon at recombination, which is determined by 0.06%. Scaling variant is ruled out at the sigma level, and this is robust against changes in the model, like running spectral index, tensor fluctuations, etc. So this is also another way to prove inflation. And then, finally, I would add here the tension that has been found also for some parameters like the Hubble constant or the matter density parameter. So this is the contents of the universe before Planck and after. So basically, a bit more of matter and a bit less of the biggest unknown, which is dark energy. Planck has also detected the lensing signal. The photons coming from the large scattering surface are deflecting by the gravitational potentials that wells that are encountered in the path from redshift 1000 to redshift 0 to the observer. This is the power spectrum of the potential lensing, and this is a reconstruction of the map of the potential. This signal is detected at the 26 sigma's confidence level. And this is to illustrate the effect of lensing on the photons is typically of 2.4 arc-minutes, and you see the shift here. The important thing is also that this is coherent, this shift, small but coherent in tens of degrees. So apart from lensing, there are other secondary anisotropies that have been detected by Planck for the first time. For instance, the integrated Schwarzschild, and these are a gravitational redshift of the photons, which is produced by the same gravitational wells than the bending of light. And there you expect a cross-correlation signal, and it's found best with the bispectrum, going to the 3-point distribution. And then this is detected at the 2.5 sigma level, as expected by the standard model. Other effects are coming from in the gas, hot gas, mainly seen in rich clusters of galaxies. Here is a picture of the distribution of this S-set effect. So, comparison with other cosmological probes, we have here that, as I said, the best measured parameter is the angular scale of the sound horizon at recombination. And there are other cosmological probes that perform surveys of galaxies, and then they can measure the same distance scale, the same meter, but at low redshift, at these redshifts here. Planck is measuring this at a redshift of 1,000. So extrapolating from Planck, this is what you expect, this gray band. And this is what has been obtained by the different surveys, 6-degree field, Sloan, Bose, Wiggle, etc. And you see that the nice agreement. Also, with Big Bang nucleosynthesis, you can see here the agreement between this vertical band from Planck, just constraining the baryonic physical density, compared to the expectation from the standard Big Bang nucleosynthesis and observations of deuterium and, helium and deuterium abundance. Also looking at a different data, this is the halo galaxy power spectrum from Sloan, 7 release. The blue line is the best fit by Planck, and the data is the Sloan data. So you see that this is a nice fit. So for the expansion rate of the universe, Planck got lower value than other measurements, especially local measurements from Cepheids and also the time delay from a gravitational system. But with this measure is a good agreement, also with WMAP. So this is the situation. And there are also internal tensions within Planck, comparing with Planck data on lensing, which is produced at low redshift. The effect is peak at redshift 2. And then data coming from Planck itself also, which is the set clusters of galaxies. So you see that lensing is in very good agreement with the expectation from the standard model, which should be 1, right? But once you don't include the lensing data, let's say, from the quartic quantity from temperature map in the analysis, you see that there is a tension between, let's say, the information at large scattering surface and the information that you get at low redshift. And the same is happening with the clusters, which is information from Planck, but at low redshift. And still, you see that the clusters tend to provide low values, as in the lensing, of the fluctuations. This is the amplitude of the fluctuations, scalar fluctuations, whereas the data at recombination tends to provide a larger value. So just continuing with precision cosmology, it's easy to see how precise can we be in relation to the scalar spectral index. And as I said, this is now very well away from scaling invariant. And by eye, you can see the difference between the blue line, which is a scaling invariant, and the actual data, which is the best fit is 0.96. This is just multiplying by L squared the power spectrum I showed you before. It's just to see it better. So when we have concordance with other probes, then we can combine them and get better results, better constraints. So this is what this table is showing. So you see here the same 6 parameters of the base standard model. And again, you see that here you had some improvement in some of the parameters, in particular related to some of the spectral index, etc., but all compatible with Planck alone, or with the CMB alone. You see the improvement better here, comparing the blue line here and for the amplitude of the fluctuations of the power spectrum, also the optical depth, and also somewhat the spectral index. So going beyond the standard model and allowing other parameters in the analysis, we see that for the curvature of space, that is, if we allow a non-zero value, then we get something which is compatible with 0. And this is determined with an error of 0.006 here in the best case, combining also with BAOs, variant acoustic oscillations, Gaussian surveys. So there is no evidence for any extension of the standard lambda CDM model. In particular, there is no evidence for curvature in space. There is no evidence for extra relativistic species beyond the three ones given by the standard model. There is no need for running a spectral index. And there is a limit on the gravitational wave parameter, which is this 0.11, below the detection claimed by BICEP. And then the dark energy equation state parameter is compatible with the cosmological constant. So there are also constraints on inflationary models. I think Alan was presenting some models in his talk. Here we have more specific models that have been provided in the literature. And in particular, the main result here for Planck is that the low field concave models are preferred compared to the large field convex models, convex potentials. And then, in particular, for monomial power laws, powers above 2, which are these, are disfavored. And there are other inflationary models, what is called natural inflation, which has an extra parameter here, f, and it seems to prefer large values of f, and this is this band here. And then you have here this an extension of general relativity, gravity theory, which is R2 inflation, which provides is very well within the range provided by Planck. So let's talk also about some issues with the analysis. In particular, it is found that the fit to the low L's in the power spectrum is not so good. So there is a discrepancy, is a deficit of power from the prediction of the standard, the best fit model. And this can be seen here. And as we will say later, this is also related to other anomalies found in the data. It's not very high significant, but it's interesting enough, I would say. So this all is mainly based until now on the two-point correlation function under the Gaussianity and isotropy analysis. Now we can check, in particular, these assumptions, these properties of the standard paradigm, by constructing a map, a clean CMB map, and this is again the potentiality of Planck, that the data can be separated between the cosmic signal and the foregrounds, as it is illustrated here. So there are 4 ways of doing this, and in particular they are based on different mathematics, and they all deal with galactic emissions and extragalactic point sources, which are described here. And normally, this part of the sky, the galactic plane, is masked together with all these point sources. It's 10. Okay, thank you. So this is the situation in temperature. So we have here the different foregrounds, and this is the CMB. There is, just to illustrate that this is real data, I mean, with the data we got, there is a window at around 100 gigahertz where the CMB dominates in this range of multipoles over the other foregrounds. This is not the case for polarization. This is the 4 renditions of the clean CMB maps that Planck has provided. They are very much consistent with each other. They are separately constructed. And with these maps, we can probe the isotropy and the Gaussianity of the fluctuations predicted by inflation. And just Nicholas Copernicus and Gauss has much to say here. So these are, as I said, main characteristics of the cosmological paradigm, and also they are assumed in the estimation of the power spectrum, in the likelihood for the power spectrum and cosmological parameters. So with these maps, we can then, in particular, perform this Gaussianity analysis. Was found compatible with Gaussianity. And also, just to revise some anomalies already shown in WMAP. And what we found is that we confirm these anomalies, in particular this alignment. This should be random and distributed between the quadrupole and octopole directions, defined this way. And you see that there is a close alignment within 8 degrees, a bit more than found by WMAP, but still is significantly interesting of 1%. I mean, not much, but it's interesting to study. Similarly, for the dipolar, there's an asymmetry in the power in 2 different hemispheres. And this is also seen up to 600 in multipoles. You can see it's also at the 3 sigma level, approximately. And the cold spot, which is a large and very cold spot, which can be seen here at 10 degrees. And again, it's all of the order of this kind of probability around, let's say, when you take into account everything, maybe 3 sigma. So what is next? The full data set results expected to be published at the end of this year. The amount of data in temperature is going to be duplicated, but the most interesting data is coming from polarization, which is the first time that is analyzed. And then the sensitivity of Planck is 0.05 in R, with the pivot value used by Planck. And the present constraint is with this pivot value, which is the same than BICEP 0.125. Then the main limitations to extract the maximum information from Planck are systematic effects, foreground contamination. In particular, a detailed study of separation of the foreground emission from the CMB signal is mandatory, and especially in polarization where the cosmic signal is weaker and the foregrounds are not well known. So this is the situation with the polarization at high multipoles. This is just a comparison with the best fit model using only temperature, which is the red line, and you see the nice fit here at high multipoles in TE and EE. And this is stacking of cold and hot and cold spots in temperature and polarization. This is real data, and this is a simulation. So the agreement is quite good already. And this is the situation with the scalar and tensor temperature observables. And in particular, I would like to stress here the weakness of the B mode that we want to detect here, is the tensor fluctuation, which is much smaller than the other scalar quantities that are all of them already detected, also the B mode lensing. So the situation, even before Planck was launched, and the reason why Planck has so many frequencies is just because of the foregrounds again. So in polarization, the situation is even worse, in the sense that, for instance, for the E mode, yes, you can see the cosmic signal in some windows in frequency around 100 and in this range without doing anything in a large fraction of the sky. Whereas for the B mode, for this value of the B mode, for instance, you see that you need to reduce both dust and synchrotron by a factor of 10 in order to see something, to see this window at around 100 GHz. And this was already the situation in 2005. So, I mean, we really need to take care of these foregrounds. And this is what Planck is doing now. This is the paper published 1 month ago, or a bit more, in which thermal dust emission, which has a which is linearly polarized and dominates at above 100 GHz, presents this complex pattern here. We didn't cover the whole sky because of the signal is weaker here, and also you have the CIB. This is for 353 GHz. And the degree of polarization shows a strong variation, which is here, with a tendency to grow at high galactic latitudes. So when you go to higher latitudes, lower dust column densities, you see that the degree of polarization increases. So we still have to see what happens here, but the tendency is already this. And then it is not clear that the CMB mode polarization can be measured directly at any region of the sky without that significant subtraction of that polarization at these frequencies, high frequencies. So motivated by the recent claim detection of the primordial gravitational wave background by BICEP, the study of the synchrotron, especially the polarized dust, is a priority now in Planck. And Planck has this capability to disentangle between the different signals. Unfortunately, we don't have the results yet, but we expect to have it in a question of few weeks, probably within a month. You will see the result, what is the dust in these regions, and in particular, in the region provided by, or probed by BICEP. So this is a summary. Planck has confirmed the standard lambda model with a high precision. No evidence is found for possible extensions of this model. The expected non-Gaussian signals have been detected at these levels. Only constraints on specific non-Gaussianity and isotropic models are provided. So in primordial non-Gaussianity from non-standard inflationary models, it's only constraints, cosmic strings, no detection, and non-trivial topology and anisotropic Bianchi models. There is a general confirmation of the W-map anomalies with Planck. And the recent analysis of foreground emissions and polarization indicate that their contribution is significant in large areas of the sky at the cosmological frequencies. Then it's only still remaining if this high dust emission is also present or not in these other regions where BICEP has been observing. But as I said, this is something that Planck has the capability to disentangle, to see if this is due to dust or not. And this is something that very soon will provide the results. Thank you.
So, thank you. Questions or comments? It's hard to see from here. No? Yes.
Just a question about the difference between the baryon density seen by the Planck experiment and what is measured with the deuterium abundance.
And deuterium abundance?
Yes, there is some tension between the recent BBN estimation and Planck 1.
Yes. So the deuterium abundance is this range here. This is
deuterium downstairs. There is the direct measurement of Pettine and Cook.
Yeah, but this is here. So it's
yes.
with agreement with Planck here and with the expectation from Big Bang nucleosynthesis, I would say. So it's quite compatible. We don't consider this any tension.
Yes, there.
When you say that in a few weeks you're going to come out with some clarification, is that going to be a part of the joint thing that he was, or it's not going to be a part of that?
No, this is only Planck.
That will just be independent of?
This is only Planck. So okay. This is a publication by Planck on the dust emission expected and high galactic latitudes, and just the regions that are uncovered in the previous paper, and then in particular the expectation for the BICEP region. Right.
Yes, there in the middle.
So in the Planck cosmological constants paper, the effective number of neutrinos, NF, changes when you consider when you change Planck basically H, and there's some inconsistencies between the Planck measurement of H and some ground-based measurements, as far as I remember. Is there going to be any new analysis on that, or are the cosmological constants that Planck put out the final ones from Planck?
You are talking about the cosmological constant and the...
Oh, sorry. I meant the cosmological parameters.
Okay. So you are talking about this Hubble parameter here?
Yeah.
So there is this tension between these are local measurements, low redshift measurements, compared to the high redshift ones, 1,000, redshift of 1,000. And Planck is providing the lowest value, although compatible with WMAP within 1 sigma. So yes, this is the situation, but still there are other measurements which are also at low redshift, as this measure, which is completely compatible with Planck. So in principle, the situation is this, so we have to wait. I don't think Planck is going to change much the results because, well, we'll have more data on temperature, but it is not expected a lot of changes in the parameters from Planck from temperature. Polarization is the new data, which is going to reduce the error bars significantly, and that I don't know yet.
But can it change the central values at all? Polarization?
Sorry,
Can the polarization data change the central values at all, do you think?
Yes, because many parameters are correlated. Some of the parameters are, and especially for optical depth. So if you are able to constrain better the optical depth, you then constrain better, for instance, the spectral scalar index and the amplitude of the scalar fluctuations. And then at the same time, you have something to say on the Hubble parameter, because this information is also in the polarization data. Yeah.
How can you distinguish the polarization from dust, from the primordial polarization?
Well, because two main features. One is the frequency dependence, which is different from the cosmic signal, and the other is the spatial distribution, which is different. So these two, spatial distribution and frequency dependence, Planck has both, because it's covering the whole sky, and also it has a very wide range of frequencies to see the dust, especially, for instance, in polarization at 353 gigahertz.
So you know the distribution of here.
Where are you?
I'm here.
Okay, sorry.
You know the distribution of dust then?
We have it. We know how the dust is distributed at 353, which is, sorry, this map here. No. For instance.
So how have you measured the distribution of mass of dust?
This is data. So this is the dust distribution.
How do you know that that is dust?
Because it's at 353, we know the dust dominates. That's for sure, because we see it in the data. And it dominates over most of the sky.
The frequency, it's the frequency which is typical.
Yes, the frequency.
353 megahertz, is that what you mean?
Gigahertz. Yeah,
gigahertz.
It's a higher frequency. Yeah. And with that, and modelizing appropriately, that we know how the dust more or less is behaving in frequency, and we have data at other frequencies, and then we can extrapolate and see what is the dust expected at 150, for instance, 143 for Planck.
I see. Thank you.
Yes, Tini.
I have a very naive question. I'm here.
Yes.
If I take in the temperature spectrum, I take the maximum, the height of the maximum of the first peak of Planck, and I compare to that of WMAP 7, there is a difference in height of 4 standard deviation. How can you have an idea of the reason of that?
Well, that's an interesting
It's between
question.
4 and 5 standard deviations.
Yes, so I think this is something that is being studied and analyzed and probably revised with the new data. So this is it's not a huge, it's important in standard deviations, but it's not so important for the cosmological parameters. So the impact of these differences in the cosmological parameters is small. In fact, as I have shown, WMAP is very compatible with Planck.
Yes, but
this is
still
something.
5 sigma.
Yeah, but I mean, It depends on what you are interested in. So if you are asking about the impact of this on the cosmological parameters, this is small.
No, that is not my question.
Okay. So if you
there are two experiments, both extremely precise, that different with a difference in a point or in a peak that is 5 sigma. So there is something that is not understood, I believe.
That's right. That's right. So this is something that we are analyzing now with the new data. The systematics is better and better understood, and we will revise this in the next data release.
Okay, thank you.
Okay, any other comment or question to any of the speakers? I don't see any. Well, yes, there's one there.
When you show your multipole evolution, in the left side where you have the low multipoles, your model is undershooting by about 10%, you said. And
yes.
You said it's at attention about 3%, which is fine. How much will that improve in the next iterations of Planck release? What can be expected there?
Nothing. So this is, you are here completely dominated by cosmic variance, by the fact that you only have one universe, and the number of modes at low L's is limited, it's finite. So Planck already, the instrumental error bars are much smaller now than the cosmic variance. So you are not going to improve the situation at all in these measurements. However, if you perform different fits, if this data is changed from the new release, I don't expect much changes, then of course changing the best fit model, it will change also this here. But the data is unchanged.
It's in there.
Let me try to figure out what Planck can be done in this case. Dust should be, if you analyze it, frequency dependent.
Right.
Okay? But primordial signal should not.
That's
that
right.
means if you analyze dust and you find this dependence in frequency, because you have many, since bicep 2 has only one, probably it's difficult just to reach a conclusion about that. Because imagine that you get this, when you analyze, and I'm just betting, that when you analyze in your dust, you see that it's frequency dependent. But, and the primordial signal should not be. Then how you should be able to rule out, for instance, bicep 2 in that case, because it's only one signal.
Yeah, the game here is to compare, since you have many frequency channels, you can see how the dust behaves in a given region with frequency. And you can extrapolate, because at a given frequency, you have all the emissions there. But seeing one component at a different frequency, you can see how this component translates to that frequency. And you can see how much dust emission you expect, or you see, or what is the best fit for the dust at the frequency you are interested in cosmological frequency.
Okay, yes, you want to answer?
I think it's also worth pointing out here that the spatial cross-correlation is going to be valuable between these frequencies. Right, so it's the frequency structure is certainly important for differentiating the components, but what we'll be telling of it being dust would be if you see a strong correlation between them. If you don't see a correlation between them, then that also is indicative that that's not the right answer. So, that's really where the joint analysis I think is going to derive a lot of its power.
Yeah, well, this is basically to monitor the dust at different frequencies. And we have all the information. We have the information at different frequencies. We have the information in all the sky. So we can see if the behavior of the dust is understood or not, in a sense. It's as much as one can do with the dust.
Okay, one more question, and then we finish. Okay.
I just want to clarify. So suppose Planck comes out and says that the dust polarization corresponding to 150 gigahertz is 13%, to pick a random number. if there is later, is there still the possibility that a cross-correlation, and this could be to either speaker, would still show an effect, or is then the cross-correlation moot?
It is clear that the two data sets are very complementary. So BICEP has the best sensitivity at 150 GHz, whereas Planck has sensitivity at not so good at 143, which is the Planck closest frequency, but also has a lot of information from other frequencies. The combination of both data sets within a collaboration, a collaborative work, because everyone is expert on his own data, is the best approach to say the final answer to this. Maybe we will, I think, hopefully we will finish with our collaboration formalized, because the collaboration has been, talks are going on, and hopefully this collaboration will be in the near future, and then we'll come out with a combined analysis of all the data. In any case, Planck will have this paper within 1 month's time on dust, and this will be the first result on this issue. And then at the end of the year, Planck also has sensitivity to, if R is 0.2, for sure that Planck will detect it and will confirm it in October. And the final sensitivity of Planck is 0.05 in R, so still Planck has a lot to say.
Okay, I think we can finish here, and we'll be looking forward to your data for sure. Okay, thank you very much.
Thank you.
All the speakers.